then our position embedding table is going to run out of scope because it only has embeddings for up to block size. And so therefore I added some code here to crop the context that we're going to feed into self, so that we never pass in more than block size elements. So those are the changes, and let's now train the network. Okay, so I also came up to the script here and I decreased the learning rate because the self-attention can't tolerate very, very high learning rates. And then I also increased the number of iterations because the learning rate is lower. And then I trained it, and previously we were only able to get to up to 2.5, and now we are down to 2.4. So we definitely see a little bit of an improvement from 2.5 to 2.4 roughly, but the text is still not amazing. So clearly the self-attention head is doing some useful communication, but we still have a long way to go. Okay, so now we've implemented the scale.product attention. Now next up in the attention is all you need paper. There's something called multi-head attention. And what is multi-head attention? It's just applying multiple attentions in parallel and concatenating the results. So they have a little bit of diagram here. I don't know if this is super clear. It's really just multiple attentions in parallel. So let's implement that. Fairly straightforward. If we want a multi-head attention, then we want multiple heads of self-attention running in parallel. So in PyTorch, we can do this by simply creating multiple heads. So however many heads you want, and then what is the head size of each. And then we run all of them in parallel into a list and simply concatenate all of the outputs. And we're concatenating over the channel dimension. So the way this looks now is we don't have just a single attention that has a hit size of 32, because remember, n embed is 32. Instead of having one communication channel, we now have 4 communication channels in parallel. And each one of these communication channels typically will be smaller correspondingly. So because we have 4 communication channels, we want 8-dimensional self-attention. And so from each communication channel, we're getting together 8-dimensional vectors, and then we have 4 of them, and that concatenates to give us 32, which is the original n embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution, because basically, instead of having one large convolution, we do convolution in groups, and that's multi-headed self-attention. And so then here, we just use SA heads, self-attention heads instead. Now, I actually ran it, and scrolling down, I ran the same thing, and then we now get this down to 2.28 roughly. And the output is still, the generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communications because we have an embed. And so this is kind of similar to, if you're familiar with convolutions, this is kind of like a group convolution because based on scrolling down, I ran the same thing, and then we now get this down to 2.28 roughly. And the output is still, the generation is still not amazing, but clearly the validation loss is improving because we were at 2.4 just now. And so it helps to have multiple communication channels because obviously these tokens have a lot to talk about. They want to find the consonants, the vowels, they want to find the vowels just from certain positions, they want to find any kinds of different things. And so it helps to create multiple independent channels of communication, gather lots of different types of data, and then decode the output. Now, going back to the paper for a second, of course, I didn't explain this figure in full detail, but we are starting to see some components of what we've already Oh, implemented. We have the positional encodings, the token encodings that add. We have the masked multi-headed attention implemented. Now, here's another multi-headed attention, which is a cross attention to an encoder, which we're not going to implement in this case. I'm going to come back to that later. But I want you to notice that there's a feed-forward part here, and then this is grouped into a block that gets repeated again and again. Now, the feed-forward part here is just a simple multi-layer positron. So the multi-headed, so here position-wise feed-forward networks is just a simple little MLP. So I want to start basically in a similar fashion, also adding computation into the network. And this computation is on a per node level. So I've already implemented it, and you can see the diff highlighted on the left here when I've added or changed things. Now before we had the multi-headed self-attention that did the communication, but we went way too fast to calculate the logits. So the tokens looked at each other, but didn't really have a lot of time to think on what they found from the other tokens. And so what I've implemented here is a little feed-forward single layer. And this little layer is just a linear followed by a relu nonlinearity, and that's it. So it's just a little layer. And then I call it feed-forward and embed. And then this feed-forward is just called sequentially right after the self-attention. So we self-attend, then we feed-forward. And you'll notice that the feed-forward here, when it's applying linear, this is on a per token level. All the tokens do this independently. So the self-attention is the communication, and then once they've gathered all the data, now they need to think on that data individually. And so that's what feed-forward is doing, and that's why I've added it here. Now, when I train this, the validation loss actually continues to go down, now to 2.24, which is down from 2.28. The outputs still look kind of terrible, but at least we've improved the situation. And so as a preview, we're going to now start to intersperse the communication with the computation. And that's also what the transformer does when it has blocks that communicate and then compute, and it groups them and replicates them. Okay, so let me show you what we like to do. We'd like to do something like this. We have a block, and this block is basically this part here, except for the cross attention. Now the block basically intersperses communication and then computation. The communication is done using a multi-headed self-attention, and then the computation is done using a feed-forward network on all the tokens independently. Now, what I've added here also is, you'll notice, this takes the number of embeddings in the embedding dimension and the number of heads that we would like, which is kind of like group size in group convolution. And I'm saying that the number of heads we'd like is 4. And so because this is 32, we calculate that because this is 32, the number of heads should be 4. The head size should be 8, so that everything sort of works out channel-wise. So this is how the transformer structures sort of the sizes, typically. So the head size will become 8, and then this is how we want to intersperse them. And then here, I'm trying to create blocks, which is just a sequential application of block, 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 so that we're interspersing communication feed-forward many, many times, and then finally we decode. Now, I actually tried to run this, and the problem is this doesn't actually give a very good answer, a very good result. And the reason for that is we're starting to actually get like a pretty deep neural net. And deep neural nets suffer from optimization issues, and I think that's what we're kind of like slightly starting to run into. So we need one more idea that we can borrow from the transformer paper to resolve those difficulties. Now, there are 2 optimizations that dramatically help with the depth of these networks and make sure that the networks remain optimizable. Let's talk about the first one. The first one in this diagram is, you see this arrow here, and then this arrow and this arrow. Those are skip connections, or sometimes called residual connections. They come from this paper, the Procedural Learning for Image Recognition, from about 2015, that introduced the concept. Now, these are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier, addition distributes gradients equally to both of its branches that fed as the input. And so the supervision or the gradients from the loss basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time and are used to project that's it. These are basically, what it means is you transform the data, but then you have a skip connection with addition from the previous features. Now, the way I like to visualize it, that I prefer, is the following. Here the computation happens from the top to bottom, and basically you have this residual pathway, and you are free to fork off from the residual pathway, perform some computation, and then project back to the residual pathway via addition. And so you go from the inputs to the targets only via plus and plus and plus. And the reason this is useful is because during backpropagation, remember from our micrograd video earlier, addition distributes gradients equally to both of its branches that fed as the input. And so the supervision or the gradients from the loss basically hop through every addition node all the way to the input, and then also fork off into the residual blocks. But basically you have this gradient superhighway that goes directly from the supervision all the way to the input, unimpeded. And then these residual blocks are usually initialized in the beginning, so they contribute very, very little, if anything, to the residual pathway. They are initialized that way. So in the beginning, they are sort of almost kind of like not there. But then during the optimization, they come online over time, and they start to contribute. But at least at the initialization, you can go from directly supervision to the input. Gradient is unimpeded and just flows, and then the blocks over time kick in. And so that dramatically helps with the optimization. So let's implement this. So coming back to our block here, basically what we want to do is we want to do x equals x plus self-attention and x equals x plus self.feed forward. So this is x, and then we fork off and do some communication and come back. And we fork off and we do some computation and come back. So those are residual connections. And then swinging back up here, we also have to introduce this projection. So nn.linear, and this is going to be from, after we concatenate this is the size n embed. So this is the output of the self-attention itself, but then we actually want the to apply the projection, and that's the result. So the projection is just a linear transformation of the outcome of this layer. So that's the projection back into the residual pathway. And then here in the feed forward, it's going to be the same thing. I could have a self.projection here as well, but let me just simplify it, and let me couple it inside the same sequential container. And so this is the projection layer going back into the residual pathway. And so that's it. So now we can train this. So I implemented one more small change. When you look into the paper again, you see that the dimensionality of input and output is 512 for them. And they're saying that the inner layer here in the feed forward has dimensionality of 2048. So there's a multiplier of 4. And so the inner layer of the feed forward network should be multiplied by 4 in terms of channel sizes. So I came here and I multiplied 4 times embed here for the feed forward, and then from 4 times n embed coming back down to n embed when we go back to the projection. So adding a bit of computation here and growing that layer that is in the residual block on the side of the residual pathway. And then I trained this, and we actually get down all the way to 2.08 validation loss. And we also see that the network is starting to get big enough that our train loss is getting ahead of validation loss. So we start to see like a little bit of overfitting. And our generations here are still not amazing, but at least you see that we can see like is here, this now, grieve, sync. Like this starts to almost look like English. So yeah, we're starting to really get there. Okay, and the second innovation that is very helpful for optimizing very deep neural networks is right here. So we have this addition now, that's the residual part. But this norm is referring to something called layer norm. So layer norm is implemented in PyTorch. It's a paper that came out a while back here. And layer norm is very, very similar to bash norm. So remember back to our Make More series part 3. We implemented bash normalization. And bash normalization basically just made sure that across the bash dimension, any individual neuron had unit Gaussian distribution. So 0 mean and unit standard deviation, 1 standard deviation output. So what I did here is I'm copy pasting the bash norm 1D that we developed in our Make More series. And see here we can initialize, for example, this module, and we can have a batch of 32 100-dimensional vectors feeding through the bash norm layer. So what this does is it guarantees that when we look at just the 0th column, it's a 0 mean, 1 standard deviation. So it's normalizing every single column of this input. Now the rows are not going to be normalized by default because we're just normalizing columns. So let's now implement layer norm. It's very complicated. Look, we come here, we change this from 0 to 1. So we don't normalize the columns, we normalize the rows. And now we've implemented layer norm. So now the columns are not going to be normalized, but the rows are going to be normalized. For every individual example, its 100-dimensional vector is normalized in this way. And because our computation now does not span across examples, we can delete all of this buffers stuff because we can always apply this operation and don't need to maintain any running buffers. So we don't need the buffers. There's no distinction between training and test time. And we don't need these running buffers. We do keep gamma and beta. We don't need the momentum. We don't care if it's training or not. And this is now a layer norm. And it normalizes the rows instead of the columns. And this here is identical to basically this here. So let's now implement layer norm in our transformer. Before I incorporate the layer norm, I just wanted to note that, as I said, very few details about the transformer have changed in the last 5 years, but this is actually something that slightly departs from the original paper. You see that the add and norm is applied after the transformation, now it is a bit more basically common to apply the layer norm before the transformation. So there's a reshuffling of the layer norms. So this is called the pre-norm formulation, and that's the one that we're going to implement as well. So slight deviation from the original paper. Basically, we need two new layer norms. Layer norm 1 is nn dot layer norm, and we tell it how many, what is the embedding dimension. And we need the second layer norm. And then here, the layer norms are applied immediately on X. So self.layer norm 1 applied on X, and self.layer norm 2 applied on X before it goes into self-attention and feed forward. And the size of the layer norm here is an embed, so 32. So when the layer norm is normalizing our features, it is the normalization here happens, the mean and the variance are taken over 32 numbers. So the batch and the time act as batch dimensions, both of them. So this is kind of like a per token transformation that just normalizes the features and makes them unit mean, unit Gaussian at initialization. But of course, because these layer norms inside it have these gamma and beta trainable parameters, the layer norm will eventually create outputs that might not be unit Gaussian, but the optimization will determine that. So for now, this is incorporating the layer norms, and let's train them out. Okay, so I let it run, and we see that we get down to 2.06, which is better than the previous 2.08. So a slight improvement by adding the layer norms. And I'd expect that they help even more if we had a bigger and deeper network. One more thing I forgot to add is that there should be a layer norm here also typically as at the end of the transformer and right before the final linear layer that decodes into vocabulary. So I added that as well. So at this stage, we actually have a pretty complete transformer according to the original paper, and it's a decoder-only transformer. I'll talk about that in a second. But at this stage, the major pieces are in place, so we can try to scale this up and see how well we can push this number. Now, in order to scale up the model, I had to perform some cosmetic changes here to make it nicer. So I introduced this variable called nLayer, which just specifies how many layers of the blocks we're going to have. I create a bunch of blocks, and we have a new variable number of heads as well. I pulled out the layer norm here, and so this is identical. Now, one thing that I did briefly change is I added dropout. So dropout is something that you can add right before the residual connection back, or right before the connection back into the residual pathway. So we can drop out that as the last layer here. We can drop out here at the end of the multi-headed extension as well. And we can also drop out here when we calculate the basically affinities, and after the softmax, we can drop out some of those. So we can randomly prevent some of the nodes from communicating. And so dropout comes from this paper from 2014 or so. And basically it takes your neural net and it randomly, every forward-backward pass, shuts off some subset of neurons. So randomly drops them to 0 and trains without them. And what this does effectively is, because the mask of what's being dropped out is changed every single forward-backward pass, it ends up kind of training an ensemble of subnetworks. And then at test time, everything is fully enabled, and kind of all of those subnetworks are merged into a single ensemble, if you want to think about it that way. So I would read the paper to get the full detail. For now, we're just going to stay on the level of this is a regularization technique. And I added it because I'm about to scale up the model quite a bit, and I was concerned about overfitting. So now when we scroll up to the top, we'll see that I changed a number of hyperparameters here about our neural net. So I made the batch size be much larger, now it's 64. I changed the block size to be 256. So previously it was just 8 characters of context. Now it is 256 characters of context to predict the 257th. I brought down the learning rate a little bit because the neural net is now much bigger, so I brought down the learning rate. The embedding dimension is now 384, and there are 6 heads. So 384 divided 6 means that every head is 64 dimensional as a standard. And then there are going to be 6 layers of that. And the dropout will be at 0.2. So every forward-backward pass, 20% of all of these intermediate calculations are disabled and dropped to 0. And then I already trained this and I ran it. So drum roll, how well does it perform? So let me just scroll up here. We get a validation loss of 1.48, which is actually quite a bit of an improvement on what we had before, which I think was 2.07. So we went from 2.07 all the way down to 1.48 just by scaling up this neural net with the code that we have. And this, of course, ran for a lot longer. This maybe trained for, I want to say, about 15 minutes on my A100 GPU. So that's a pretty good GPU. And if you don't have a GPU, you're not going to be able to reproduce this. On a CPU, this would be, I would not run this on a CPU or a MacBook or something like that. You'll have to bring down the number of layers and the embedding dimension and so on. But in about 15 minutes, we can get this kind of a result. And I'm printing some of the Shakespeare here, but what I did also is I printed 10,000 characters, so a lot more, and I wrote them to a file. And so here we see some of the outputs. So it's a lot more recognizable as the input text file. So the input text file, just for reference, looked like this. So there's always like someone speaking in this manner, and our predictions now take on that form. Except, of course, they're nonsensical when you actually read them. So it is every crimpy be a house. Oh, those privation, we give heed. You know. Oh ho, sent me you, mighty Lord. Anyway, so you can read through this. It's nonsensical, of course, but this is just a transformer trained on the character level for 1 million characters that come from Shakespeare. So it's sort of like blabbers on in Shakespeare-like manner, but it doesn't, of course, make sense at this scale. But I think still a pretty good demonstration of what's possible. So now, I think that kind of like concludes the programming section of this video. We basically kind of did a pretty good job of implementing this transformer, but the picture doesn't exactly match up to what we've done. So what's going on with all these additional parts here? So let me finish explaining this architecture and why it looks so funky. Basically what's happening here is, what we implemented here is a decoder-only transformer. So there's no component here. This part is called the encoder, and there's no cross-attention block here. Our block only has a self-attention and the feed-forward. So it is missing this third in between piece here. This piece does cross attention. So we don't have it, and we don't have the encoder, we just have the decoder. And the reason we have a decoder only is because we are just generating text, and it's unconditioned on anything. We're just blabbering on according to a given data set. What makes it a decoder is that we are using the triangular mask in our transformer. So it has this autoregressive property where we can just go and sample from it. So the fact that it's using the triangular mask to mask out the attention makes it a decoder, and it can be used for language modeling. Now, the reason that the original paper had an encoder-decoder architecture is because it is a machine translation paper. So it is concerned with a different setting. In particular, it expects some tokens that encode, say, for example, French, and then it is expected to decode the translation in English. So you typically, these here are special tokens. So you are expected to read in this and condition on it. And then you start off the generation with a special token called start. So this is a special new token that you introduce and always place in the beginning. And then the network is expected to output neural networks are awesome, and then a special end token to finish the generation. So this part here will be decoded exactly as we've done it. Neural networks are awesome will be identical to what we did. But unlike what we did, they want to condition the generation on some additional information. And in that case, this additional information is the French sentence that they should be translating. So what they do now is they bring the encoder. Now the encoder reads this part here. So we're only going to take the part of French, and we're going to create tokens from it, exactly as we've seen in our video. And we're going to put a transformer on it. But there's going to be no triangular mask. And so all the tokens are allowed to talk to each other as much as they want. And they're just encoding whatever's the content of this French sentence. Once they've encoded it, they basically come out in the top here. And then what happens here is in our decoder, which does the language modeling, there's an additional connection here to the outputs of the encoder. And that is brought in through cross attention. So the queries are still generated from X, but now the keys and the values are coming from the side. The keys and the values are coming from the top, generated by the nodes that came outside of the encoder. And those tops, the keys and the values there, the top of it, feed in on a side into every single block of the decoder. And so that's why there's an additional cross attention. And really what it's doing is it's conditioning the decoding, not just on the past of this current decoding, but also on having seen the fully encoded French prompt, sort of. And so it's an encoder-decoder model, which is why we have those two transformers, and an additional block, and so on. So we did not do this because we have nothing to encode. There's no conditioning. We just have a text file, and we just want to imitate it. And that's why we are using a decoder-only transformer, exactly as done in GPT. Okay, so now I wanted to do a very brief walkthrough of NanoGPT, which you can find on my GitHub. And NanoGPT is basically two files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here. It's the training loop. It's just that it's a lot more complicated because we're saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the training.py gets a little bit more hairy, complicated. There's more options, etc. But it's a little in points training loop. It's just that it's a lot more complicated because the train.py is basically two files of interest. There's train.py and model.py. Train.py is all the boilerplate code for training the network. It is basically all the stuff that we had here. It's the training loop. It's just that it's a lot more complicated because we're saving and loading checkpoints and pre-trained weights, and we are decaying the learning rate and compiling the model and using distributed training across multiple nodes or GPUs. So the training.py gets a little bit more hairy, complicated. There's more options, etc. But the model.py should look very, very similar to what we've done here. In fact, the model is almost identical. So first, here we have the causal self-attention block, and all of this should look very, very recognizable to you. We're producing queries, keys, values, we're doing dot products, we're masking, applying softmax, optionally dropping out, and here we are pooling the values. What is different here is that in our code, I have separated out the multi-headed attention into just a single individual head, and then here I have multiple heads and I explicitly concatenate them. Whereas here, all of it is implemented in a batched manner inside a single causal self-attention. And so we don't just have a B and a T and a C dimension, we also end up with a fourth dimension, which is the heads. And so it just gets a lot more sort of hairy because we have four-dimensional array tensors now, but it is equivalent mathematically. So the exact same thing is happening as what we have. It's a bit more efficient because all the heads are now treated as a batch dimension as well. Then we have the multilayer perceptron. It's using the Gelu nonlinearity, which is defined here instead of Rolu. And this is done just because OpenAI used it, and I want to be able to load their checkpoints. The blocks of the transformer are identical, the communicate and the compute phase, as we saw. And then the GPT will be identical. We have the position encodings, token encodings, the blocks, the layer norm at the end, the final linear layer. And this should look all very recognizable. And there's a bit more here because I'm loading checkpoints and stuff like that. I'm separating out the parameters into those that should be weight decayed and those that shouldn't. But the generated function should also be very, very similar. So a few details are different, but you should definitely be able to look at this file and be able to understand a lot of the pieces now. So let's now bring things back to ChatGPT. What would it look like if we wanted to train ChatGPT ourselves, and how does it relate to what we learned today? Well, to train ChatGPT, there are roughly two stages. First is the pre-training stage, and then the fine-tuning stage. In the pre-training stage, we are training on a large chunk of internet and just trying to get a first decoder-only transformer to babble text. So it's very, very similar to what we've done ourselves, except we've done like a tiny little baby pre-training step. And so in our case, this is how you print a number of parameters. I printed it and it's about 10 million. So this transformer that I created here to create a little Shakespeare transformer was about 10 million parameters. Our data set is roughly 1 million characters, so roughly 1 million tokens. But you have to remember that OpenAI uses a different vocabulary. They're not on the character level. They use these subword chunks of words. And so they have a vocabulary of 50,000, roughly, elements. And so their sequences are a bit more condensed. So our data set, the Shakespeare data set, would be probably around 300,000 tokens in the OpenAI vocabulary, roughly. So we train about 10 million parameter model on roughly 300,000 tokens. Now, when you go to the GPT-3 paper and you look at the transformers that they trained a number of transformers of different sizes, but the biggest transformer here has 175 billion parameters. So ours is again 10 million. They used this number of layers in the transformer. This is the N embed. This is the number of heads, and this is the head size. And then this is the batch size. So ours was 65. And the learning rate is similar. Now, when they trained this transformer, they trained on 300 billion tokens. So again, remember, ours is about 300,000. So this is about a million-fold increase. And this number would not be even that large by today's standards. You'd be going up 1 trillion and above. So they are training a significantly larger model on a good chunk of the internet, and that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable to you, and the architecture is actually like nearly identical to what we implemented ourselves. But of course, it's a massive infrastructure challenge to train this. You're talking about typically thousands of GPUs having to, talk to each other to train models of this size. So that's just the pre-training stage. Now, after you complete the pre-training stage, you don't get something that responds to your questions with answers and is not helpful and etc. You get a document completer, right? So it babbles, but it doesn't babble Shakespeare, it babbles internet. It will create arbitrary news articles and documents, and it will try to complete documents because that's what it's trained for. It's trying to complete the sequence. So when you give it a question, it would just potentially just give you more questions. It would follow with more questions. It will do whatever it looks like some closed document will do in the training data on the internet. And so who knows, you're getting kind of like undefined behavior. It might basically answer with two questions with other questions. It might ignore your question. It might just try to complete some news article. It's totally unaligned, as we say. So the second fine-tuning stage is to actually align it to be an assistant. And this is the second stage. And so this ChatGPT blog post from OpenAI talks a little bit about how this stage is achieved. We basically, there's roughly 3 steps to this stage. So what they do here is they start to collect training data that looks specifically like what an assistant would do. So they have documents that have the format where the question is on top and then an answer is below. And they have a large number of these, but probably not on the order of the internet. This is probably on the order of maybe thousands of examples. And so they then fine-tune the model to basically only focus on documents that look like that. And so you're starting to slowly align it. So it's going to expect a question at the top, and it's going to expect to complete the answer. And these very, very large models are very sample efficient during their fine-tuning. So this actually somewhat works. But that's just step 1. That's just fine-tuning. So then they actually have more steps where, okay, the second step is you let the model respond, and then different raters look at the different responses and rank them for their preferences to which one is better than the other. They use that to train a reward model. So they can predict, basically using a different network, how much of any candidate response would be desirable. And then once they have a reward model, they run PPO, which is a form of policy gradient reinforcement learning optimizer, to fine-tune this sampling policy so that the answers that ChatGPT now generates are expected to score a high reward according to the reward model. And so basically there's a whole aligning stage here, or fine-tuning stage. It's got multiple steps in between there as well. And it takes the model from being a document completer to a question answerer. And that's like a whole separate stage. A lot of this data is not available publicly. It is internal to OpenAI, and it's much harder to replicate this stage. And so that's roughly what we do at ChatGPT. And NanoGPT focuses on the pre-training stage. Okay, and that's everything that I wanted to cover today. So we trained, to summarize, a decoder-only transformer following this famous paper, Attention is All You Need, from 2017. And so that's basically a GPT. We trained it on a tiny Shakespeare and got sensible results. All of the training code is roughly 200 lines of code. I will be releasing this code base. So also it comes with all the git log commits along the way as we built it up. In addition to this code, I'm going to release the notebook, of course, the Google Colab. And I hope that gave you a sense for how you can train these models like, say, GPT-3 that will be architecturally basically identical to what we have, but they are somewhere between 10,000 and 1 million times bigger, depending on how you count. And so that's all I have for now. We did not talk about any of the fine-tuning stages that typically go on top of this. So if you're interested in something that's not just language modeling, but you actually want to, say, perform tasks, or you want them to be aligned in a specific way, or you want to detect sentiment or anything like that. Basically, anytime you don't want something that's just a document completer, you have to complete further stages of fine-tuning, which we did not cover. And that could be simple supervised fine-tuning, Or it can be something more fancy like we see in ChatGPT, where you actually train a reward model and then do rounds of PPO to align it with respect to the reward model. So there's a lot more that can be done on top of it. I think for now we're starting to get to about 2 hours mark, so I'm going to kind of finish here. I hope you enjoyed the lecture, and yeah, go forth and transform. See you later. What we can do is we can now just basically apply the same language modeling loss function, but we're currently training on the yellow tokens, and we are weighing the language modeling objective by the rewards indicated by the concrete example. So let's work with a concrete example here. Let's say that you are working on an article or a blog thing. I have this separate process almost inspect token, and they can go down sort of like a blind alley in terms of reasoning. And so unlike you, they cannot recover from that. They are stuck with every single token they sample. And so they will continue the sequence even if they even know that this sequence is not going to work out. So give them the ability to look back, inspect, or try to basically sample around it. Here's one technique also. You could, it turns out that actually LLMs, like they know when they screwed up. So as an example, say you ask the model to generate a poem that does not rhyme. And it might give you a poem, but it actually rhymes. But it turns out that especially for the bigger models like GPT-4, you can just ask it, did you meet the assignment? And actually GPT-4 knows very well that it did not meet the assignment. It just kind of got unlucky in its sampling. And so it will tell you, no, I didn't actually meet the assignment. Here, let me try again. But without you prompting it, it doesn't even, like it doesn't know to revisit and so on. So you have to make up for that in your prompts. You have to get it to check. If you don't ask it to check, it's not going to check by itself. It's just a token simulator. I think more generally, a lot of these techniques fall into the bucket of what I would say recreating our system 2. So you might be familiar with the system 1, system 2 thinking for humans. System 1 is a fast automatic process, and I think kind of corresponds to like an LLM just sampling tokens. And system 2 is the slower, deliberate planning sort of part of your brain. And so this is a paper actually from just last week, because this space is pretty quickly evolving. It's called Tree of Thought. And in Tree of Thought, the authors of this paper propose maintaining multiple completions for any given prompt. And then they are also scoring them along the way and keeping the ones that are going well, if that makes sense. And so a lot of people are like really playing around with kind of prompt engineering to basically bring back some of these abilities that we sort of have in our brain for LLMs. Now, one thing I would like to note here is that this is not just a prompt. This is actually prompts that are together used with some Python glue code, because you actually have to maintain multiple prompts, and you also have to do some tree search algorithm here to like figure out which prompts to expand, etc. So it's a symbiosis of Python glue code and individual prompts that are called in a while loop or in a bigger algorithm. I also think that there's a really cool parallel here to AlphaGo. AlphaGo has a policy for placing the next stone when it plays Go, and its policy was trained originally by imitating humans. But in addition to this policy, it also does multi-correlate tree search. And basically, it will play out a number of possibilities in its head and evaluate all of them and only keep the ones that work well. And so I think this is kind of an equivalent of AlphaGo, but for text, if that makes sense. So just like Tree of Thought, I think more generally, people are starting to like really explore more general techniques of not just a simple question-answer prompt, but something that looks a lot more like Python glue code, stringing together many prompts. So on the right, I have an example from this paper called React, where they structure the answer to a prompt as a sequence of thought, action, observation, thought, action, observation, and it's a full rollout, kind of a thinking process to answer the query. And in these actions, the model is also allowed to tool use. On the left, I have an example of AutoGPT. And now AutoGPT, by the way, is a project that I think got a lot of hype recently. But I think I still find it kind of inspirationally interesting. It's a project that allows an LLM to sort of keep a task list and continue to recursively break down tasks. And I don't think this currently works very well, and I would not advise people to use it in practical applications. I just think it's something to generally take inspiration from in terms of where this is going, I think, over time. So that's kind of like giving our model system 2 thinking. The next thing that I find kind of interesting is this following sort of, I would say, almost psychological quirk of LLMs, is that LLMs don't want to succeed.
They want to imitate. You want to succeed, and you should ask for it. So what I mean by that is, when transformers are trained, they have training sets. And there can be an entire spectrum of performance qualities in their training data. So for example, there could be some kind of a prompt for some physics question or something like that, and there could be a student solution that is completely wrong, but there can also be an expert answer that is extremely right. And transformers can't tell the difference between like they know about low quality solutions and high quality solutions, but by default, they want to imitate all of it because they're just trained on language modeling. And so at test time, you actually have to ask for a good performance. So in this example, in this paper, they tried various prompts, and let's think step by step was very powerful because it sort of like spread out the reasoning over many tokens. But what worked even better is let's work this out in a step-by-step way to be sure we have the right answer. And so it's kind of like conditioning on getting a right answer, and this actually makes the transformer work better because the transformer doesn't have to now hedge its probability mass on low-quality solutions, as ridiculous as that sounds. And so basically, feel free to ask for a strong solution. Say something like, you are a leading expert on this topic. Pretend you have IQ 120, etc. But don't try to ask for too much IQ, because if you ask for an IQ like 400, you might be out of data distribution. Or even worse, you could be in data distribution for some like sci-fi stuff, and it will start to like take on some sci-fi, like role-playing or something like that. So you have to find like the right amount of IQ. I think it's got some U-shaped curve there. Next up, as we saw, when we are trying to solve problems, we know what we are good at and what we're not good at, and we lean on tools computationally. You want to do the same potentially with your LLMs. So in particular, we may want to give them calculators, code interpreters, and so on, the ability to do search. And there's a lot of techniques for doing that. One thing to keep in mind, again, is that these transformers by default may not know what they don't know. So you may even want to tell the transformer in a prompt, you are not very good at mental arithmetic. Whenever you need to do very large number addition, multiplication, or whatever, instead use this calculator. Here's how you use the calculator. Use this token combination, etc., etc. So you have to actually like spell it out because the model by default doesn't know what it's good at or not good at necessarily, just like you and I might be. Next up, I think something that is very interesting is we went from a world that was retrieval only all the way, the pendulum has swung to the other extreme where it's memory only in LLMs. But actually there's this entire space in between of these retrieval augmented models, and this works extremely well in practice. As I mentioned, the context window of a transformer is its working memory. If you can load the working memory with any information that is relevant to the task, the model will work extremely well because it can immediately access all that memory. And so I think a lot of people are really interested in basically retrieval augmented generation. And on the bottom, I have like an example of llama index, which is one sort of data connector to lots of different types of data. And you can index all of that data, and you can make it accessible to LLMs. And the emerging recipe there is you take relevant documents, you split them up into chunks, you embed all of them, and you basically get embedding vectors that represent that data. You store that in the vector store, and then at test time, you make some kind of a query to your vector store, and you fetch chunks that might be relevant to your task, and you stuff them into the prompt, and then you generate. So this can work quite well in practice. So this is, I think, similar to when you and I solve problems. You can do everything from your memory, and transformers have very large and extensive memory, but also it really helps to reference some primary documents. So whenever you find yourself going back to a textbook to find something, or whenever you find yourself going back to documentation of a library to look something up, the transformers definitely want to do that too. You have some memory over how some documentation of a library works, but it's much better to look it up. So the same applies here. Next, I wanted to briefly talk about constraint prompting. I also find this very interesting. This is basically techniques for forcing a certain template in the outputs of LLMs. So guidance is one example from Microsoft, actually. And here we are enforcing that the output from the LLM will be JSON. And this will actually guarantee that the output will take on this form because they go in and they mess with the probabilities of all the different tokens that come out of the transformer, and they clamp those tokens. And then the transformer is only filling in the blanks here. And then you can enforce additional restrictions on what could go into those blanks. So this might be really helpful, and I think this kind of constraint sampling is also extremely interesting. I also wanted to say a few words about fine-tuning. It is the case that you can get really far with prompt engineering, but it's also possible to think about fine-tuning your models. Now, fine-tuning models means that you're actually going to change the weights of the model. It is becoming a lot more accessible to do this in practice, and that's because of a number of techniques that have been developed and have libraries for very recently. So for example, parameter-efficient fine-tuning techniques like LoRa make sure that you're only training small, sparse pieces of your model. So most of the model is kept clamped at the base model, and some pieces of it are allowed to change, and this still works pretty well empirically, and makes it much cheaper to sort of tune only small pieces of your model. It also means that because most of your model is clamped, you can use very low precision inference for computing those parts because they are not going to be updated by gradient descent, and so that makes everything a lot more efficient as well. And in addition, we have a number of open source high quality based models. Currently, as I mentioned, I think Llama is quite nice, although it is not commercially licensed, I believe, right now. Some things to keep in mind is that basically fine-tuning is a lot more technically involved. It requires a lot more, I think, technical expertise to do right. It requires human data contractors for data sets and/or synthetic data pipelines that can be pretty complicated. This will definitely slow down your iteration cycle by a lot. And I would say, on a high level, SFT is achievable because it is just you're continuing the language modeling task. It's relatively straightforward. But RLHF, I would say, is very much research territory and is even much harder to get to work. And so I would probably not advise that someone just tries to roll their own RLHF implementation. These things are pretty unstable, very difficult to train, not something that is, I think, very beginner-friendly right now, and it's also potentially likely also to change pretty rapidly still. So I think these are my sort of default recommendations right now. I would break up your task into two major parts. Number one, achieve your top performance, and number two, optimize your performance, in that order. Number one, the best performance will currently come from GPT-4 model. It is the most capable model by far. Use prompts that are very detailed. They have lots of task contents, relevant information and instructions. There's a large number of limitations. Power is accessible at your fingertips. So here's everything that's needed in terms of code to ask GPT-4 a question, to prompt it and get a response. In this case, I said, can you say something to inspire the audience of Microsoft Build 2023? And I just punched this into Python, and verbatim, GPT-4 said the following. And by the way, I did not know that they used this trick in the keynote, so I thought I was being clever, but but it is really good at this. It says, ladies and gentlemen, innovators and trailblazers of Microsoft Build 2023, welcome to the gathering of brilliant minds like no other. You are the architects of the future, the visionaries molding the digital realm in which humanity thrives. Embrace the limitless possibilities of technologies and let your ideas soar as high as your imagination. Together, let's create a more connected, remarkable, and inclusive world for generations to come. Get ready to unleash your creativity, canvas the unknown, and turn dreams into reality. Your journey begins today. Okay.